And so remember, line lever birth is just it's called the double reciprocal plot because you take the Michaelis-Menten equation. So if you remember, the Michaelis-Menten looks like, whenever you plot it out, it looks like this. And its velocity is a function of substrate. And what's that shape going to be? It's hyperbolic. And so something like that. Of course, the asymptote that approaches is Vmax. Half of Vmax, that concentration is Km. But if you can do what's called double reciprocal plot, which is where you take the reciprocal of each section, and if you do that, it turns a hyperbolic function into a line. So especially in the old days when they drew this all by hand, they would always do double reciprocal plots. Not always, but they would usually do double reciprocal plots because it's relatively easy then to determine like what the y-intercept is and what that means and the x-intercept and everything like that. And so that's what this figure is just showing up. It's just showing. Okay, and once again, the Km is the dissociation constant for all, technically speaking, it's for all bound enzyme species. So it's similar to Kd, or the dissociation constant. Okay? And so that's why if it's a really low Km, that means the substrate is going to bind really tightly. If it's a larger Km, it doesn't bind nearly as tightly. Okay, Vmax is related to turnover number, which is the kcat. That's maximum velocity. If you know your enzyme concentration, then you can actually literally solve for the catalytic rate constant. If you don't, which in vivo a lot of times we don't know the actual enzyme concentration, then you use Vmax. But once again, it gives you an idea of how fast, what's the fastest turnover, the fastest amount, or how quickly you can make product. It doesn't necessarily mean that's most efficient, and that's what we discussed in the car example on Wednesday. Instead, for catalytic efficiency, that's the kcat over Km, or Vmax over Km, depending upon whether or not you know enzyme concentration. Okay, so this is just an example of showing like what some of the Kms and kcats are. And then once again, the specificity constant technically is a second order rate constant, but it tells you the efficiency or how efficient it is for that enzyme for that specific substrate. Because a lot of times what you do is you have an enzyme that may have more than one substrate, but it has different kcat over Kms. So it'll be more efficient for one versus the other. Okay, and this gives some examples of what some of these are. And you always have to look to see, oh, it doesn't say here what the units are, but this is from the old book. Many enzymes have multiple substrates, and so there are a couple of different ways that you can bind more than one substrate. The first two form what's called the ternary complex. That's when you have three things bound at the same time. Okay, so that literally means 3 in 1. And so you can have what's called random, which what random means is there are two substrates and you're going to make one or two products, and you can bind them. It doesn't matter which order you bind them. You can bind that what they call substrate 1 or substrate 2 first to make this is the ternary complex, and then you get release of your products. Or you can also have it to where it's ordered, and you must bind one substrate before the second substrate, but you still have that ternary complex, and then you get your product or products. Okay, so those are the ones that involve a ternary complex, but there's actually another one that happens a lot of times. In fact, next semester when we go over the mechanism for the aminotransferase, it does Watson B, which is called a ping-pong mechanism. It's also known as a double displacement. Okay, and so what happens here is you don't get a ternary complex. Instead, what you get is a covalent modification of the enzyme. Let me erase this off. And so first happens is it binds the first substrate to make the first Michaelis complex. And like for example, in the aminotransferase, maybe the first amino acid comes in to bind, and then it adds the nitrogen, the amino group, to the enzyme, and so then the first product leaves. But now this enzyme has been modified somehow because it's got the extra amino group on it. Then the second substrate comes in, that's the pong part of the ping and pong, and it comes in, binds that modified enzyme, and it takes the amino group off the enzyme to make the second product, and you get your enzyme back. And so that's why it's like back and forth. That's why they call it ping pong or double displacement. Okay. So that one's actually quite common as well. Another example of the ping pong type of mechanism would be a lot like the serine proteases, for example, or even cysteine proteases, where they go in and they take the big protein at first and they break it. And so then part of that protein, the peptide, is stuck to the enzyme, and then the water or the nucleophile comes in and it takes it off and takes the second piece off of it, and you get your enzyme back. So now we're going to talk about enzyme inhibition. And I want you to know different types of enzyme inhibition inhibitors, and also like what effects that they have on KCAT, KM, and KCAT over KM, or Vmax, KM and Vmax over KM. Okay, so I'm actually going to start with so that you can imagine that there are two really broad classes. There are those that are reversible inhibitors. We'll break that down. And then there are the irreversible. And if it's an irreversible inhibitor, they're usually called, or sometimes they're called suicide inhibitors, because if it's irreversible, that enzyme is dead. You can't get it back. So we don't talk a lot about the irreversible ones, other than the fact that once that enzyme has been modified with that inhibitor, it's no longer functional. So that's why it's called a suicide inhibitor. The enzyme has been killed. Okay, and usually that's going to be where the enzyme has been covalently modified, or to where, and it can't be detached from. Okay, whereas reversible means it can come on and off. And so it can inhibit the enzyme, but it doesn't kill the enzyme. Okay, so just to reiterate, reversible means it just binds transiently, but it can be released. And there are three types, well, technically four. There are three types, and then the fourth one is mixed. Okay, now I want you to know all of these, and we're going to see how they affect the Michaelis-Menten and the Lineweaver-Burke plots. So we have competitive inhibitor, which means it's going to compete with the substrate. So typically we're talking about it binds either active site, catalytic site, get off the substrate, or binds to where the active site can no longer accept substrate, where it causes some type of conformational change. Okay. Whereas non-competitive means it binds somewhere, it has to bind somewhere other than the active site. It changes the conformation, but it's not competing at all with substrate. It's just now that the enzymes can't function. Even if substrate binds, it can't function. And I've got cartoons that kind of show this as well. Then there's uncompetitive, which means it binds to the Michaelis complex. So therefore, it doesn't compete at all with substrate binding. In fact, it can only recognize the ES complex. That's uncompetitive. And then mixed is just a mixture of competitive and uncompetitive. A little mixture of things. All right. So we're first going to talk about competitive inhibition. This is just a little, oh, that's the irreversible once again. This is just a little tiny cartoon that came from the original book that we used to use, but it's overly simplistic. But you can see here that in the absence of inhibitor, that's where the substrate binds in that little jagged spot, whereas a competitive inhibitor binds to the same spot. Non-competitive means that it binds someplace else and just makes it to where the substrate is unlikely to bind. Your book uses this kind, which I actually like a little better because it gives you the reaction equation as well. So that way you can clearly see how it binds to the free enzyme. And the equilibrium constant that they use is called Ki, and this truly is a Kd. Okay, so that's really the dissociation constant for the inhibitor. And so you can see it's competing in what it does is it swipes some of the free enzyme away, so there's less free enzyme for the substrate to bind. So that's why it's competing with it. Okay. So what this means is, if we think about it, let me see if I can, let me erase those. And we look at the Lineweaver-Burke, first. So remember, that's V over, well, the concentration of S. And this is what it normally would look like. So we have Vmax is at asymptote. So I'm going to draw it right out here, Vmax. That's without any inhibitor. What this means is that any substrate that binds will eventually, once it binds, it can go on and make product. So that means ultimately it's going to have the same Vmax. It's just much more difficult for the substrate to bind. So because of that, it's going to make it, I'm going to do it in this color. Oops, no. There we go. So we get the same Vmax. But if we now look at the KIs, not the KIs, the KMs, whatever this color is, that's the KM for it. So it's further to the right. Whereas the Km for the uninhibited is at the same height, but it's a much lower substrate concentration. So this is the Km for the uninhibited. That would be the Km for the inhibited. And I say Km, technically it's Km apparent, because once again, Km is for all enzyme-bound intermediates. So that's why it takes that EI into consideration. So it shifts that Km, the apparent Km, towards the right. So it makes it look like the substrate is binding less tightly. In reality, the reason why the substrate is binding less tightly is because it's having problems getting to the active site. It's too crowded. There's already an inhibitor there. So you can override this inhibition by just adding more and more and more substrate. Okay, so that's what it looks like on the Lineweaver-Burke. I mean, on the Michaelis-Menten. Let's see what it looks like on the Lineweaver-Burke. So I'm going to actually leave the Michaelis-Menten there. So on Lineweaver-Burke, remember, this is what it looks like. It's 1 over V, and on the x-axis is 1 over S. That would be without inhibitor, is that color. And so the Vmax technically is 1, it's 1 over Vmax, that's the y-intercept. So this one, sometimes it's hard for me to draw, especially draw a straight line. It's going to have the same y-intercept. It's going to look like that. So it's going to cause the slope of the line to go that way. And the reason why is, remember, the slope, M, is equal to, instead of Vmax over Km, it's Km over Vmax because it's reciprocal. And so that's the reason why it makes it look steeper. But it's going to have the same 1 over Vmax. This is the y-intercept. No, Mx plus B. That's the B. And the negative 1 over Km is going to be closer to 0 because the Km is getting larger, and so that's why it's going to make it look smaller and smaller and smaller. Like this thing is, it's like going down. All right. There we go. So this is just the word showing what I said already, and how it's competing with the substrate. They just got it all going in the same line, it's just going down. And how the dissociation constant is called Ki, and this is free enzyme times free inhibitor divided by the EI complex. And then they show you why that happens to the Lineweaver-Burke. Okay, and so you can see that you get that 1 plus 1 I over Ki. You're going to see that term pop up from time to time. I don't ask you to memorize this. In your book, I think even calls it like alpha prime or something like that. And then they just say, well, alpha prime is equal to 1 plus I over Ki. Yep.
So why does the slope change again on the Lineweaver-Burke? Yeah, the Lineweaver-Burke, because it's 1 over Vmax, however Vmax doesn't change.
Right.
So why does your slope change?
The slope changed because the Vmax over Km part changed. So here, let me show you. Let me see if I can. I mean, I got used to seeing it on Michaelis-Menten because that's what, in enzymology, that's really what we use. So if you look at the Michaelis-Menten plot, And I'm going to really blow it up this time. Okay, so that's V, this is S. So on here, that asymptote is going to be Vmax. You go 1/2, you go, oh, whoa, that's really crooked. Chords get in the way. You go over, you hit the line, and you go down. That's Km. The part that's kind of hard to see whenever you draw it small is if you take the slope of this line, this part of the line right here, remember that's the tangent as it approaches 0, that, the slope of that is Vmax over Km. Okay. So now what happens when, and this is whenever you do the line Weaver Burke, it's a little easier. What happens is it's Km over Vmax, and it becomes literally the slope of the line. What happens though is once we add the inhibitor, use a different color. It's going to have the same Vmax eventually, but the Km now is further over. So I'm going to put a little I next to it. So that's in the presence of inhibitor, or you could say K prime M or whatever. But now if we look at that slope of the tangent, let's see. I don't know if this color, will this color show up? Yeah, okay. So now if we look at the slope there, that's the slope for Vmax over Km there. Right, and then what happens is whenever you do line Weaver Burke, you flip them both over, and so that's the reason why it becomes Km over Vmax and everything. So that's why the apparent slope changes. It's easier to see that slope, the K cat over Km slope, or the reciprocal of it, on the line Weaver Burke than it is on this, but this way has less error. So whenever we do this in the lab next semester, we'll use either Cladograph or maybe even Mathematica, because universities think about buying Mathematica, in order to fit this for us, so that way you don't have to try to do it by hand or anything like that. It'll fit, do the global fitting for you, make nice pretty graphs, like the kind that you actually see in papers. And you can't do this with Excel. Excel doesn't handle, I mean, it can handle a line, and that's pretty much it. And even then, it doesn't really do linear regression, right? It does trend lining, but, you know, so that's just not what Excel was made for. All right, so that's why the competitive inhibitor looks like on the line Weaver Burke. More substrate is needed in order to compete with the inhibitor in order for the product to form. Next step is uncompetitive. Remember, that's the one that only affects the Michaelis complex. And so uncompetitive is a little different. So what we see here is even if the substrate binds, doesn't necessarily mean it's going to go to the same, it can't go to the same Vmax. It's going to be slowed down because even though the substrate's binding, the inhibitor binds and yanks it down to where it's no longer active. And so that's why this little cartoon. So what happens here is it's going to affect both the K-cat or Vmax and the Km. Because remember, Km is substrate binding, and now we've got, instead of having just free substrate and ES, we have free substrate ES and ESI. So it's going to affect the Km that way. It's going to affect the Vmax because even if the substrate binds, it cannot necessarily go on to make product. And so this is the hardest one for me to draw, especially to draw it well. But I'll try. So if we look at the Michaelis-Menten, oh, that's not the right color. Do a different color. We look at the Michaelis-Menten plot. Once again, it's V over S. That's supposed to be an S, but it got cut off. So there, this is without inhibitor. So we get our Vmax. With the inhibitor, what happens is you have the same apparent Vmax over Km. So the slope down here is the same, but you get a different Vmax and a different Km. And so that's the Vmax plus the inhibitor. And then the Km is going to be different for both of these. The Km for this one, so this is Vmax. Oops, that's a little too low. So you go 1/2 there, you go over, you go down. So that's the Km in the presence of the inhibitor. And then if we look at the Km in the presence of the, or of the normal Km, whoops, mine got really close, but it's going to be a little further to the left. Okay, it's easy to see this one on the line with Burke, because if you remember, the slope has to do with the Vmax over Km, and so they have the same slope, so it makes parallel lines. So I definitely can't draw a parallel line straight, so I'm just going to show you what that one looks like. So this is a Lineweaver Burke, if it's uncompetitive. See, your book likes that alpha prime, and all that alpha prime means is that 1 plus I over Ki. It's just easier for them to write. It looks, more simple. It's that factor, the inhibitor factor. So the apparent Kms are affected, as is the apparent Vmaxes. Okay. Then there's the mixed inhibition, which is just a little mixture of both. So the inhibitors binds anything, everything. It shows all properties of all the inhibitors. And so it looks really cool. I can't do it justice on Michaelis-Menten plot. And so I'll only show you on the Lineweaver Burke. But it looks like this, where they all intersect, but they don't intersect on any of the axes. It's in that upper left quadrant, usually. Okay? And so that's why that 1 plus I over Ki, that alpha prime factor, is on both the Km over Vmax part and the 1 over Vmax part. That alpha prime is that, if you read in your book and everything, it's in the one that I showed earlier, the very first one. There's this thing that shows, and I don't have you guys do the math to figure out, but if you actually solved for it, it's this. That's equal to alpha prime. It's 1 plus the concentration of I over the Ki. That's what the little alpha thing is. Then we have non-competitive. Remember, non-competitive doesn't interfere with the binding of the substrate. So Km is the same, but Vmax has changed. Okay, so the reason, the way that looks, and you can keep adding more and more and more substrate concentration, but you can't overcome the non-competitive inhibitor. Since it's got the same Km, it's kind of hard to draw well on the Michaelis-Menten, but I'll try. It's really easy to see it on the Lineweaver Burke. Vs. So we have Vmax. And there's Km. Well, now we have to have the same Km, but we have a different Vmax. So let's see. Let's say that. Oops. if that's the halfway point, then that's going to be the maximum point. There we go. So it's got the same Km, but it has a different Vmax. Actually, that turned out a lot better than what it normally does. But you can, because if you remember, on the Lineweaver-Burke, it's the x-intercept that shows you where Km is. And so you're going to have the same x-intercept and different y-intercepts. So that's why it's really easy to see this one on the Lineweaver-Burke. I'll show you what that looks like in just a moment.
When you're drawing that line from the y-axis over to your hyperbolic,
Yeah.
and then bringing it down to your x-axis for your Km value, how do you know where to start on your y-axis?
It's at the halfway point, the half of Vmax. So if you just imagine Vmax being at 100, then you start at the point at 50. If your Vmax was at 80, then you would start at 40 and go over. This literally means 50% of Vmax. And so the non-competitive looks like this. It has the exact same x-intercept, but it's going to have differing y-intercepts. Whereas the competitive has the same y-intercepts but different x-intercepts. And the uncompetitive, they all intersected, but not on either axis. Okay. So that's why, if we try to make a little table, so we have the type of inhibitor, we've got the competitive inhibitor, we've got the non-competitive inhibitor, and then we've got the uncompetitive inhibitor, and of course mixed just means a mixture of these. If we think about Vmax or Km, and then Vmax over Km. Whoa, that K got really freaky. So what happened is, or what happens, is that for the competitive inhibitor, remember there was no change. So there's no change on Vmax. So once the substrate bound, it could go on to make the regular product. It was just that the Km apparently increased because it looks like it gets bigger and bigger and bigger. So if you take the same number and you divide by a bigger number, it's going to make the Vmax over Km apparently decrease for a competitive inhibitor. The non-competitive inhibitor had no change at all for the Km, but the Vmax decreases. So then you're dividing in Vmax over Km, you're going to take a smaller number on the top and divide by the same number. So that means overall it's going to decrease. The uncompetitive, there is no change here. Vmax and Km both decrease apparently. Vmax gets slower, Km looks a little lower. And the reason why the Km looks a little lower is because now, instead of having just ES and then the ES complex, you have E times S divided by ES plus ESI. So that's the reason why it looks like it's getting tighter binding, but in reality it's not so much as getting tighter binding, it's just like there's one more additional thing that can be bound. And so that's the reason why it, overall, it comes out looking like there's no change. Okay. Are there any questions on this before we start talking about how that they're used, how that they are used for disease markers? And I've just picked a couple of examples. Questions? Yes. Yes. Mm-hmm. I mean, it won't have my notes. Because even though it save the notes that I handwrite in there, for whatever reason, PowerPoint doesn't. only the video does. So, okay. Let me just put all this up because I don't want to have to. I don't actually like this slide because it's too wordy. But, all right. But you can actually have enzymes are many times used for looking at disease and disease markers. In fact, whenever you go in for a blood panel, I'm sure some of you probably have, then a lot of the things that they're testing for are the presence of specific enzymes. Because if you have certain disease states or if certain tissues are damaged, then the concentration of these enzymes increase in your bloodstream. Okay, and so what they do, for example, the lactate dehydrogenase is the LDH. Okay, so there are different isoforms or different versions of that enzyme in your heart versus your regular skeletal muscle. And what happens is if the muscle starts to break down, then it can't hold on to its LDH, or for example, if you're having heart problems or whatever, then the cardiac version of the LDH in the blood will increase. There's been some tissue damage. Or vice versa, in theory, with the muscle. Okay. All right, and the reason why, and they can tell the different isoforms because they have different KMs for they do the same reaction, because dehydrogenase, does anyone remember for what kind of reactions are dehydrogenases? Pardon? I can't hear you.
Don't they just take the hydrogen off and then put it back on whenever?
No, not necessarily. Like the broad classes of enzymes. Dehydrogenases are the ones that you usually utilize NAD, NADH, or NADP, and NADPH. Those are the cofactors that are involved in those types of reactions. They do redox reactions. Okay, and so these are just going to oxidize or reduce. Okay, and the heart type has a very high KM, so that means it doesn't bind the substrate nearly as well. And it uses it for aerobic metabolism, that's why well oxygenated. Whereas the muscle type has a really, really high affinity for it because it needs to be able to convert it under anaerobic conditions to make lactate or lactic acid. Okay, and that's because you're exercising so fast with your muscles, skeletal muscles, that it doesn't have time to recharge the oxygen. Whereas you don't want to deprive your heart of oxygen. So they have different types, because what happens here is lactate dehydrogenase is LDH. This is the NADH one, and what you'll find out for next semester, because we'll see like these all the time. So that's why if you memorize your enzyme classes, like their families, you can usually tell exactly the kind of reactions that they do. It's named lactate. It's named after one of its substrates. And it just takes pyruvate, where does pyruvate come from? Does anyone know? Pardon? Glycolysis is one of the major ones. It's the end product of glycolysis from step 10. Does anyone know where else does it come from? Well, and if you look at it, it maybe you can tell it comes from one of the amino acids. Does anyone know what amino acid can make pyruvate? Because an amino acid, what are the functional groups on amino acids? Carboxylic acid, and we've got that already. There's the carboxylic acid, and then what else is there? The amine group on the C alpha. That's the C alpha, so that would be where the amine group is from the aminotransferase. So what's that R group? It's alanine. So alanine aminotransferase makes pyruvate. Or if you need to make alanine, you can actually take pyruvate and turn it into alanine. And so that's the kind of, you'll see that over and over and over again. The alanine aminotransferase is one that goes between pyruvate and alanine. So that's one way that you can just take. You don't have to have sugar, but you can have protein, and you can turn proteins into intermediates to get energy from it. Okay, but that's beside the point. But no, so you can also utilize this. The muscles can utilize the pyruvate, turn it into lactate in order to do anaerobic oxidation. But you don't want to do that with your heart. Okay. And another one is acetylcholinesterase, which is ACE or ACE, and it's for nerve impulses. So they usually, or one way that they can test for certain types of pesticides that have done nerve damage is by looking to see if there's an increase with the acetylcholinesterase. A lot of the aminotransferases, whenever you see the AST and ALT tests, like if you go in for your liver panel, those are just aminotransferases. And what happens is when you have liver problems, those, you're going to find out the liver is what does a lot of the metabolic work in your body. And so the concentration of those two aminotransferases go way, way up. So if you have an elevated AST or ALT, that's indicative of having liver damage. And then, of course, we have that, this is just one example, but there are lots and lots and lots of examples of using enzyme inhibitors as medical treatments. And now, in fact, this slide is outdated, but now, for example, with HIV or AIDS, so there are three main enzymes in HIV. Well, what is HIV, first of all? Is it really a virus, or is it a retrovirus? Okay, so it's RNA-based. No, it's not DNA-based. All right, so it has three main enzymes. One is HIV protease, which what do proteases do? They break down proteins. The other one's HIV integrase, which what do you suppose an integrase is going to do? No, that's a good one. But no, it actually integrates the retroviral genetic code into the host genetic code. And then there's a polymerase, okay, which obviously is going to make polymers. So what happens now is whenever they first started, they started to look at and trying to make inhibitors for the HIV protease that wouldn't affect the cell's regular proteases. And so scientists have made inhibitors that bind or that specifically block the HIV protease. And those examples are the ritonavir and tenofovir. But now they actually have, one of the reasons why the mortality rate for HIV in developed countries at least is really, really low is because they now do a cocktail therapy where they now have inhibitors for each of those steps, okay? Or they tried to have an inhibitor for the integrase and for the polymerases and for the protease. And by doing that, then you can keep the viral load much lower, okay? So the person can live a relatively healthy, normal life nowadays. Now, one of the very first treatments that they had were actually nucleotide or nucleoside analogs, okay? And that's one of the reasons why those medications had really, really bad side effects, because that was affecting the polymerase, but we have lots of polymerases in our bodies, and so it was also affecting regular polymerases too. So that's why they wanted to start looking at some of these other enzymes that HIV utilizes and to try to target them instead or in conjunction with, so that way you don't have to only go after the polymerase and have the bad side effects. All right, and this is just a quick little review. Nucleophile. What does every nucleophile must have? Lone pair of electrons, because that's what goes out and does the attack. Remember, the nucleophile is what does the attacking. That's why it shows that the arrow is going and attacking something. So we can have hydroxyls, okay, so the alcohols or the hydroxylate, which is whenever it becomes, the alkoxide. For example, serine, whenever it loses that hydrogen, becomes an alkoxide. You can have, what amino acid would this one be from, the second one be from? That's cysteine. And if you remember from Organic Chem 2, is sulfur a better or worse nucleophile than oxygen? It's better. It's even better, both as a leaving group and as a nucleophile. So that's why cysteine gets used a lot. You can have a carbanion. Usually the carbanion is activated, and so it's temporary because the carbon doesn't like to be negatively charged. You could have the nitrogen. So what's an amino acid that can look like this? There's one in particular that does it a lot. Arginine can to a smaller extent. What's the one that really it really is just an amine group? Lysine. And of course we have imidazole, which can be a nucleophile, and it can also be an electrophile. And that one should be fairly simple. What amino acid is that one? It's histidine, and of course you can actually have hydroxide. Now usually in our body we just don't have free hydroxides floating all over the place, so that'd be bad. And so they're usually associated with water, held between water and metal, so it's like a metal hydroxide. So it's localized. typically. Then we have the electrophiles. Those are things that, get attacked, and those are going to be the carbonyl groups, and we have lots of examples of those. I mean, every amino acid, technically every peptide can be a carbonyl, but you also have, your carboxylic acids, your amides, and things like that. You can have the protonated imine, which that one's usually done with